Welcome. This video is going to go over solutions to problems on the Chapter 6 quiz over reaction rate. So question number 1, consider the reaction between gaseous iodine and gaseous hydrogen. So you see you have I2 plus H2 yielding 2HI in a reversible reaction. Enthalpy is -9, so it's exothermic. And the question says, why do some collisions not result in the formation of product? And remember, there's 3 requirements. They have to collide, they have to have sufficient energy, or at least have activation energy, and they have to have the right orientation. So when you look at these 4 choices, A says they do not have sufficient energy, which would be correct. Equilibrium has nothing to do with it. Temperature would actually give you more collisions with more energy. And low activation energy would also make more collisions successful. So the only one that would account for not having successful collisions would be A. Number 2 talks about the Haber process to convert hydrogen and nitrogen into ammonia. And then the real question is about which statements are correct for this equilibrium state. So it's really all about equilibrium, not so much about the Haber process. So what you should know about equilibrium is that the catalyst of the forward and reverse reactions are equal. The catalyst increases the rates equally. 2, it does not affect the equilibrium constant. That's also true. And 3, the catalyst increases the yield. That is not true. A catalyst, remember, acts on increasing the rate of both the forward and reverse reactions, so there's no effect on delta H or the yield. So A, 1 and 2 would be true. Number 3, which statement describes the action of a catalyst? Again, very similar to the question we just had, a catalyst lowers activation rate for both the forward and reverse reaction. So 1, it does not alter delta H, that's true. 2, it increases activation energy. That's false. It actually decreases activation energy. And 3, it alters the mechanism or pathway of a reaction. That's true. That's why the activation energy decreases, is it provides an easier pathway or mechanism. So B would be my correct choice. Number 4, which statement is true about using sulfuric acid as a catalyst? So again, really doesn't matter what kind of reaction you're talking about. The idea that you're using a catalyst means that 1, the rate of the reaction is going to increase. 2, it lowers the activation energy. That's also true. And 3 is just the opposite. Instead of the catalyst being consumed, the catalyst remains unchanged at the end of the reaction. So 1 and 2 only are true, or letter A. Number 5, excess magnesium was added to a beaker of aqueous hydrochloric acid. A graph of the mass of the beaker and contents was plotted. So here's the original on 1 here. Just going to make a note that this is the original. What experiment could give line 2? So line 2, you have to notice that the rate is somewhat faster, and the yield is also more. So we got 2 things going on. It's not just faster, but the yield has increased as well. So A, the mass of magnesium in smaller pieces, that would not affect the yield or the mass, because magnesium was already in excess. B, the same volume of a more concentrated solution of hydrochloric acid, that would increase rate and it would increase yield, because now you have more of the limiting reactant and in a more crowded space. C, a lower temperature, that would actually decrease the rate. It wouldn't affect the yield. And then D, a more accurate instrument to measure the time, that's not going to affect our yield or our rate, simply how good our data is. So B would be my best choice. Number 6 talks about powdered manganese oxide increasing the rate. So manganese oxide is a catalyst. So 1 says the rate is independent of the particle size of MnO2. That's not true. It's not independent. It is dependent on the particle size, because smaller is better for both the catalyst and the reactants. MnO2 provides an alternative reaction pathway with a lower activation energy. That's true. That is exactly what a catalyst does. And 3, all the MnO2 is present after the decomposition of the hydrogen peroxide is complete. That's also true, because a catalyst may be altered during the reaction, but at the end of the reaction, it's there in its original form. So C, 2 and 3 would be true. Number 7, at 25 degrees, so there's my temperature. I have 200 centimeters cubed of a 1 molar nitric acid solution added to 5 grams of magnesium powder. If the experiment's repeated using the same mass of magnesium powder, so that's not going to be a factor, which conditions will result in the same initial reaction rate? So if I look, changing my volume from 200 to 100, that should have no effect. Volume is not going to affect the reaction rate. It will affect my yield. If I have a greater volume, the same rate will continue for twice as long, but this will have no effect on the yield. So any of these is possible. So then if I look at concentration, if my original was 1 molar, increasing to 2 molar would increase my yield. So I can see that A and C are not possible because of the increase in concentration. Temperature, increasing the temperature will also increase my rate and possibly my yield. So B isn't possible. So only D, where I've cut the volume in half but kept the concentration and temperature the same, should give me the same initial reaction rate. Number 8, which factors can affect reaction rate? The state of the reactants, yes, because that will influence the crowding as well as the movement of the particles. 2, the frequency of the collisions between particles, yes. And 3, the average kinetic energy of the particles, yes. So D, all 3 of these can influence reaction rate. Number 9, a piece of zinc was added to aqueous nitric acid, and here's our reaction rate plotted below. And they want to know which graph would you expect if the same mass of powdered zinc was added to nitric acid with the same concentration. So the difference is that I had a solid piece of zinc, and now my zinc is going to be more available. So my yield should be the same. The amount of product I get should be the same, but what's going to be different is my rate should be much faster. So line A here is the one I would expect, the change I would expect to see. So in this experiment, they describe Alex and Anna were asked to investigate the kinetics of the rate with these 2 reactants, propanol and iodine, forming a new product, a hydrohalogen there. And so then they were each asked to give a hypothesis. And Alex says that the rate is affected by the change in the concentration of both reactants. And Hannah says that the catalyst is involved in the concentrations of the reactants and the hydrogen ion, the catalyst will affect it. And so they want to know whether either hypothesis is correct. And this was worth 2 marks. And what you had to realize is neither is fully correct. Only the one reactant affects it. I2, the rate stayed the same even when I increased the concentration moving across here. So I2 doesn't seem to have any effect on reaction rate. So apparently that's the one that's in excess. So the propanol definitely is affecting the rate, and so is the catalyst. So each was partially correct, neither was fully correct. Why does the rate increase with increasing temperature? 2 big things. You have more collisions, so an increased frequency of collisions, and because each collision is carrying more energy, more collisions will have the minimum energy or exceed the activation energy and be successful. Part C, the reaction uses a catalyst. Sketch and annotate the Maxwell-Boltzmann, okay? So the Maxwell-Boltzmann is when you look at number of molecules versus energy. And the idea is that most of the molecules fall under this bell-shaped curve, and then there's this run out here where the activation energy actually lies, and under normal conditions, only this small number of molecules have that minimum energy. And so what happens with the catalyst? The catalyst lowers the bar. Now suddenly only this much energy is needed to be successful. And so now we add this many more successful collisions and increase the reaction rate. So on the curve, they expected you to be able to properly label the axes, have the correct shape of the line, and then be able to show how activation energy changes on the graph with and without the catalyst. Describe how it works. You could have simply said it lowers activation energy, or it provides an easier pathway. Number 11, which changes increase the reaction rate below? An increase of pressure. Well, that's only going to be true if there's a greater number of moles on the reactant side. And if I look, I do have 2 moles of gas on the reactant side and just 1 mole on the product side. So yes, an increase of pressure will speed up the rate. Increase of temperature always speeds up the rate. Removing HCl, which is a product, that would increase our yield, but that will not affect the rate. So A, 1 and 2 only would be true. And number 12, define the term activation energy. It's just the minimum energy to result in a reaction or to produce product or result in a successful collision. But it's that minimum energy needed. B, we omitted that one because we'll cover that in a minute here with another question. But C, sketch an enthalpy level diagram to describe the effect of a catalyst on an exothermic reaction. So an enthalpy diagram is when you contrast enthalpy or energy over time of the reaction. So you start with the reactants and the products. Since they ask for exothermic, the products have to lie lower on the enthalpy diagram than the reactants. That's your first mark here. And then the axes should be correctly labeled. And then your second line should indicate with the catalyst what happens is the energy needed to get to this transition state is lowered, so the bar has been lowered here. So you should have drawn in the dotted line showing that it's going to be lowered whether you're coming from product to reactant or reactant to product. Either direction, that threshold has become lower. Number 13, factors that affect the rate of a chemical reaction include particle size, concentration of reactants, and temperature. So define the rate. It's a change in reactant over time or the change in product over time, or you could be more specific and say the decrease in concentration of reactant or the increase in concentration of product over time. The three characteristic properties of reactant particles, what they mean by that is that you have to have collisions. Collisions have to possess minimum energy or the activation energy, and they have to have hit with the correct orientation. Number 14, graphing is an important method in the study of the rates. Sketch a graph to show how the reactant concentration changes with time in a typical chemical reaction taking place in solution. So what they wanted you to indicate on this graph is because it's reactant, you have to have a downward slope, a negative slope, and you have to show that exponential curve showing that the initial rate at the beginning is the steepest slope, and then the rate immediately starts slowing down as fewer reactant particles are available. So you got a line, a point for the line. You also got a point for correctly labeling your axes as concentration and time for 14 there. And then the second part they want to know, show how the rate of reaction at a particular time can be determined. And what I was trying to show on my graph to the right is, if I'm interested at time here, so right here on the graph, this is the time that I want to know the rate for. What I would have to do is draw a line tangent to this point, and then I'd have to extend down from 2 points on that line and come up with my change in time. And for those same 2 points, find my change in concentration. So I'd have delta, my change in concentration, my change in time, and I could go ahead and calculate my rate of reaction at that particular time. Number 15, skipping the first one and going to the second, state an equation for the reaction of magnesium carbonate with dilute hydrochloric acid. So MgCO3 plus 2HCl, you're going to get MgCl2 because it's a double replacement reaction. And then you can see I started writing H2CO3, but anytime you have a carbonate, that H2CO3 actually breaks apart into H2O and CO2. So I have 3 products there. The rate of this reaction can be studied using volume of gas. What would the graph look like? Since it just says sketch, this is just a 1 mark. You didn't have to label axes. You just have to show a positive slope with an exponential curve to the graph. And then the last question, the experiment is repeated using a sample of hydrochloric acid with double the volume but half the concentration. So if I had 1 molar, well, 1 molar and I had 1 liter of it, I would expect to have 1 mole of HCl. If I doubled that to 2 liters, but it was only 0.5 molar, I still have 1 mole of HCl. So what's changed? Well, my amount of product is going to be the same, but it's going to be slower to get there. So now my rate is going to go much slower, but eventually it's going to end up at the same place or the same yield. And that's what I was trying to show with my line here. And that's what you were supposed to explain, is that the yield would be the same, but the rate would be slower because you have the same number of hydrochloric acid molecules spread out in a greater space or volume.